All right, these are your notes for 6.5 law of cosines. Law of cosines is going to be used for some very specific cases, just like law of sines. So for these problems, you'll have a side angle side combination or a side 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 combination. There shouldn't really ever be an issue about memorizing cases because you can't do a law of sines problem with law of cosines formulas and vice versa. Like take a side angle side and try to do a law of sines on it. Well, it wouldn't work because you don't have a pair of angle side opposite to even get you started. And of course, side, 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 same thing. How would you just do a law of sines? You have no angles at all. So the cases, yeah, it's nice to know them, which cases go to which formulas, but you won't be able to do one with the other, so that should make it pretty easy to figure out. Law of cosines are formulas that have a little bit more going on. They're not a proportion. They're more of a kind of a multiple part formula to them. The side length formula, which is the first one you see, is pretty typical. There really are three versions of it, but it's not three different formulas. It's the same formula with the letters shuffled around. So the key for you guys is to connect the angle to the side opposite. That should be how I know what angle to plug in. So if I'm trying to find side A, I should plug in angle A. Now if you're doing B, side B, then you just got to reorganize the letters. So if it's B, well then it's going to be AC, AC, and B. And if it's C, it's going to be AB, AB, and C. So the formula is really the same formula with the letters just reshuffled depending on what side I'm trying to find. The angle formula actually comes from the side formula, so I'm going to show you guys where it comes from. If you take this formula and you square both sides, you get that. Now solve that for cosine of A. Subtract the B and C to the other side, divide by negative 2BC. You'd have cosine of A. That's not exactly the way the formula looks because we get the negative out of the denominator and kind of reshuffle it a little bit. But if you do clean that up, it's going to look like that. So there's your angle formula. Now the angle has a sort of a matching idea too. Whatever the angle is that you're trying to find should correspond to the side you're subtracting. And so that's how I know I've got things in the right spot. I always make sure, actually a lot of times for me, the first side I'll put in is the one that matches the angle, so I know I'm subtracting the correct one. The other two, the lettering, or how you put them in doesn't even make a difference because it's addition. So you don't need to get hung up on the letters so much, but what's the correspondence? Angle to the side I'm subtracting in the formula. Again, there are three versions of that formula, but that's just a matter of reshuffling the letters to match what angle you're trying to find. So if I'm trying to find B, then I'll subtract B. Try to find C, subtract C in the bigger formula. Otherwise, most of the work will be done right in your calculator. It's just a matter of plugging in and go. What's nice about the law of cosines is there's no ambiguous case. There are always one triangle problems. One more thing I would tell you guys is students are sometimes tempted when they start in the law of cosines after the first calculation to switch over to the law of sines because they think the law of sines formula is easier or simpler or whatever. Problem is when you do that, and you're starting a side, 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 or a side angle side, and you find, like, say, another angle, or you find another side, but usually it's the other angle that's going to cause the problem. You're switching to law of sines, and you're in a side, side angle mode, and you don't even know it. So what that means is you're working in the ambiguous case in a problem that doesn't have two triangles. And a lot of times what happens is you're calculating the information for a non-existent triangle number 2. So the moral of the story is, even if you weren't following my explanation, is don't switch. You start the problem in law of cosines all the way through. Same thing, law of sines, stay in law of sines all the way through. If you don't switch between the two, you'll never have an issue. But switching, especially law of cosines to law of sines, creates a problem that you wouldn't even realize is going on. Okay, so we're going to do one basic law of cosines problem, and then the rest are word problems because there isn't much to show you with a law of cosines. So clearly I have a side, side, side. So what that means is I'm going to have to calculate a couple angles first, and then the third angle I will just go subtraction from 180. So let's get them set up. So again, when I do A, I want to make sure that A is the y subtract. And when I do B, I want to make sure B is the y subtract. After that, it doesn't really make a difference how I plug the other two in because it's addition. The order is not important for addition. Now, like yesterday with the law of sines, you're doing an angle calculation. So what you need to do to get the angle is the inverse cosine of that expression, which will give you angle A. And the inverse cosine, again, down here. That calculation should be able to go into your calculator in one shot. What you'd want to do as grouping symbols is inverse cosine, you're going to get a parenthesis on your calculator. The entire numerator in a set of parentheses divided by the denominator in a set of parentheses. Hit enter, should be good. Again, remember you got to be in degree mode. We're talking about getting your angles in degrees. Without me actually showing you the, I don't know if I've got them here. Oh, there we go, there they are. Okay. So there's the three angles. You can kind of double check your calculations, make sure that you're on track and you're able to get the answers. But the first two by law of cosines formula, the third is just subtraction from 180 because you got two of the three angles in a triangle. Okay, like I said, law of cosines as just a non-word problem is pretty straightforward. Go into the formulas. All right, well, we're going to switch over to the word problems here for a few minutes. Just show you a couple and that'll be it. Kind of a short set of notes today. So your word problems are based on two concepts. There's heading and there's bearing. Heading is the actual direction you are heading. So, for example, if I'm driving from Eden Prairie to Chan on Highway 5, I'm headed west. Now, some of you guys might be out driving around having no clue what direction you're heading, north, south, east, west, but you just know where to go. I get that. Some people are not very good with directional stuff when they're driving. But the heading is based on the actual direction. Now, if you head to on the northeast, northwest, southeast, southwest, those actually are going to create a very specific kind of angle. If I'm in any one of those four spots, it's 45. So if you read a word problem, it says, you know, I'm headed due west for so many miles, then I turn and change direction and go northeast. While you're changing direction, that angle you create is going to be a 45-degree angle. So heading is where you're headed. Bearings, on the other hand, is a little bit different. Bearings are designed to read from north or south because you have no visual point of reference. There's two basic places where this will happen. One is on the ocean, one is up in the air like in a plane. And typically it'd be like probably in cloud cover where you don't see stars, you don't see the sun or the moon, so you don't have any kind of point of reference. You're on the middle of the ocean, there's cloud cover, there's not another anything, land, another ship in sight. So you have no clue really directionally, like your brain won't go, well, that is north, that is, you know, it won't do that, right? So when you got land references, then you can say, well, okay, I know that this lies north of this, so I got a reference. So when that's the case, when we don't have that reference, we go bearing. Bearings are from north or from south in the direction of east or west, and that's how we describe them. So if I look at the first one there and read it to you, north 70 degrees west, that's from north. So starting at north, 70 degrees in the direction of west. So instruments on planes and ships are based on bearings, north and south, like from a compass reading. And so that's basically how bearing works. Pretty easy to, as far as looking at these diagrams, the key is when you're drawing your diagram, it goes along with it. Where do the angles go, inside or outside the triangle? A lot of times bearing angles are outside the triangle. Okay, so bearing heading, right? Bearing from south in the direction of east or west, from north in the direction of east or west. So let's go ahead and take a look at a bearing problem. Well, sorry, a heading problem first, then a bearing problem. So this says a car is traveling along a straight road headed west. 3 hours, then travels northeast on another road for 2 hours. It maintains a constant speed. How far is it from its starting position? So first of all, you're going to have to sketch a diagram to go with this, starting by going west. So car travels west. Changes direction, goes northeast, which means you're going to create a 45. Our question is, how far are we, I should say, from the spot where we started. Now you notice that you're not given any distances. You've got speeds and times. So now you got to use the idea of distance equals rate times time, which you guys should all know. So if we're going 3 hours at 55 miles per hour or 2 hours at 55 miles per hour, there's your distances. Now, once the diagram is laid out, headed driving west, change direction northeast, create a 45, get your distances in, look at the combination of parts. Side angle side combination of parts, so it's a side angle side formula for finding the side length of a triangle to figure out what x is. This can also be put in your calculator in one shot. So you go square root, you're prompted with a set of parentheses on your calculator, which would be like this. Then what I probably would do is group those two together minus group those two together, then close off my square root. Should be able to handle that all in one shot, hit enter, answer. Okay, and so it's 116.9 roughly, so you guys can check your calculation. So a heading problem, again, well, like all of these word problems that involve triangles, right? It's all about a sketch. You get a good sketch going, it shouldn't be that hard. And I think the heading sketches are pretty easy. The bearing sketches have a little more thought in the angle aspect of it, so we're going to do that next and go through one of those. So 2 ships leave port at 9 a.m., one travels at a bearing north 53 degrees west at 12 miles per hour, the other south 67 degrees west for 16 miles per hour. Approximately how far apart are they at 12 p.m.? So a couple things. You know, when you start out getting your bearing lines in, you've got to go from north 53 degrees in the direction of west. From south 67 degrees in the direction of west. So those are your bearings, from north towards west, from south towards west. How far apart are they at 12 p.m.? Now again, you got speeds and time. 9 a.m., 12 p.m., 3 hours. 3 hours at 12 miles per hour, 3 hours at 16 miles per hour. So it looks kind of like a side angle side, but the thing that's missing would be what's the angle right in here. But you guys should recognize that from north to south, is 180 degrees. If I want that angle in there, all I really have to do is subtract 67 and 53 from a 180, and I should be able to get the third angle. Now, as soon as you have that, again, another side angle side combination of parts. So not like this problem is necessarily difficult to set up. It has to occur to you that the bearings are not inside the triangle. Okay, I'm going to show you one more bearing question, and then we're going to be done with the notes, and that'll be it for notes for today. So this one's about a sailboat race, and sailboat racing is, I don't know if you guys have ever heard of America's Cup or not that exciting to watch when they're just on the straightaways, but all the excitement will happen at the turns. And when the sailboat makes a turn, which is usually marked by a buoy in the water, the idea is to make the turn as fast as possible and get the ship on the straightest line to the next buoy. That's a bearing. So the captain and the crew needs to know when we turn the boat, what bearing do we have to get it on, and that's what they want. When they're on that bearing, then they're just going to start sailing again. But it's around the turns where all the action happens. A lot of times the crew just goes nuts to get the turn made. Sails go down, whip the boat around, sails go back up, get on that bearing, continue in the race. So this one describes a triangular course with 3 legs to it, an ABC buoy. So basically we're going to lay out the course, start at A, headed west. It doesn't tell you much else about headings. It just says that C lies north of A and B. Now the reason I've got it closer to A is because the BC leg is the longer part of the race. So it just makes sense to draw it that way.